On November 27, 1971, acoustic sensors positioned along the Greenland-Iceland United Kingdom gap detected an anomalous submarine signature transiting southward from the Barents Sea into the Norwegian Sea. The acoustic profile did not match any known Soviet submarine class catalogued in NATO intelligence databases. Analysis of propeller blade rate frequencies, machinery tonals, and hydrodynamic flow noise indicated a vessel substantially smaller than conventional Soviet nuclear attack submarines, yet exhibiting speed characteristics that exceeded performance parameters for any submarine force in the world. American sonar operators tracking the contact through the SOSUS surveillance network reported sustained speeds approaching 40 knots submerged, velocities that intelligence assessments had concluded were physically impossible for nuclear-powered submarines given reactor power limitations and hydrodynamic drag constraints. The contact designated Alpha by NATO intelligence represented the first confirmed detection of Soviet Project 705 Lira, a submarine class that fundamentally challenged every assumption Western naval planners held about underwater warfare capabilities. The strategic implications became clear during subsequent tracking operations when American attack submarines attempted intercept missions against Alfa-class vessels operating in international waters. USS Sturgeon SSN 637, conducting routine surveillance of Soviet naval activity near the Kola Peninsula in March 1972, established sonar contact with an unidentified submarine at range exceeding 15,000 yards. Commander James Fitzgerald ordered an approach to close contact for acoustic signature collection and visual identification through periscope observation. The Soviet submarine, subsequently confirmed as an Alfa-class vessel, detected the American approach and initiated evasive maneuvers. Sturgeon increased speed to pursue, but the target accelerated to velocities that placed it beyond effective tracking range within minutes. Post-mission analysis indicated the Soviet submarine sustained speeds exceeding 40 knots for more than 20 minutes, performance that should have demanded reactor power outputs beyond what intelligence assessments calculated Soviet engineering could achieve in a pressure hull small enough to maintain reasonable hydrodynamic efficiency. The confidence Soviet naval architects invested in Project 705 emerged from technological breakthroughs achieved through decades of research into exotic materials and propulsion systems. Traditional submarine construction employed high-strength steel alloys that provided adequate structural integrity while remaining economically feasible for series production. Steel hulls imposed operational depth limitations around 400 meters for most Western submarines and approximately 500 meters for advanced Soviet designs. Exceeding these depths required thicker hull plating that increased displacement, reduced internal volume, and created hydrodynamic penalties degrading speed and maneuverability. Soviet metallurgists pursuing alternatives to steel focused on titanium alloys that offered strength-to-weight ratios superior to any ferrous material. Titanium Grade 5, designated VT5 in Soviet nomenclature, provided tensile strength approaching 900 megapascals while weighing only 56% as much as equivalent steel structures. The material enabled construction of lighter pressure hulls that maintained structural integrity at greater depths or alternatively permitted thinner hull sections that reduced displacement and hydrodynamic drag. The engineering challenges associated with titanium fabrication deterred Western submarine designers from pursuing large-scale applications. Titanium exhibited extreme reactivity with atmospheric gases at elevated temperatures, requiring specialized welding procedures conducted in inert atmospheres to prevent contamination that degraded material properties. The Soviet Union developed argon-shielded welding techniques and constructed dedicated fabrication facilities where entire submarine pressure hulls could be assembled under controlled environmental conditions. The Sudomik shipyard in Leningrad established titanium fabrication capabilities in the early 1960s, accumulating expertise through construction of experimental vessels before committing to series production. By 1968, Soviet engineers possessed sufficient confidence in their titanium fabrication processes to authorize Project 705 construction employing complete titanium pressure hulls. The propulsion system selected for Project 705 represented even more radical departure from conventional submarine engineering. Standard pressurized water reactors employed in both American and Soviet submarines circulated ordinary water through reactor cores, operating at temperatures around 300 degrees Celsius and pressures exceeding 150 atmospheres. The water transferred thermal energy to steam generators that produced steam-driving turbine machinery connected to propeller shafts. This approach required substantial reactor volumes to contain primary cooling loops, steam generation equipment, and shielding that protected crew compartments from radiation. Soviet designers pursuing compact high-power propulsion examined liquid metal cooling systems that eliminated conventional steam generation entirely. Lead-bismuth eutectic, a mixture of 45% lead and 55% bismuth by weight, remain liquid at temperatures exceeding 125 degrees Celsius while providing thermal conductivity superior to water. A liquid metal-cooled reactor could operate at higher power densities within smaller containment volumes, generating more shaft horsepower from lighter machinery that occupied less internal space. The specific reactor configuration, installed aboard Project 705 submarines designated BM-40A, employed lead-bismuth coolant, circulating through a compact reactor core containing highly enriched uranium fuel assemblies. The system generated 155 megawatts thermal output converted into 40,000 shaft horsepower, extraordinary power density, that enabled a submarine displacing only 2,300 tons surfaced and 3,200 tons submerged to achieve speeds exceeding 43 knots. Comparable American attack submarines displacing 4,700 tons employed pressurized water reactors generating 15,000 shaft horsepower and achieved maximum speeds near 30 knots. The Soviet power advantage was staggering. Project 705 delivered nearly 3 times the power-to-displacement ratio of contemporary Western designs. Soviet naval doctrine anticipated that this performance margin would prove decisive in combat scenarios, where speed determined tactical advantage. The operational depth capability provided by titanium construction complemented speed advantages through enabling maneuvers beyond the performance envelope of pursuing vessels. Project 705 submarines could safely operate at depths approaching 400 meters with design crush depth estimated near 600 meters, substantially deeper than the 300-meter operational depths characterizing most NATO attack submarines. When detected by adversary forces, an Alfa-class commander could dive steeply while accelerating to maximum speed, exploiting superior depth capability to break contact while outrunning pursuing torpedoes. NATO anti-submarine warfare doctrine presumed that once sonar contact was established, attack submarines could maneuver into weapons employment range and prosecute targets with torpedoes that guaranteed destruction of any submarine unable to escape the engagement zone. Project 705 invalidated those presumptions through combining speed and depth performance that placed it beyond the capability envelope of every weapon NATO forces carried. The crew complement required to operate Project 705 represented another revolutionary aspect of the design. Conventional nuclear attack submarines employed crews numbering 100 to 130 personnel distributed among engineering, weapons, sonar, navigation, and command functions. Project 705 achieved full operational capability with only 31 crew members, a reduction enabled through extensive automation of reactor control, damage control, and ship handling functions. The automated systems employed analog computers and electromechanical controllers that managed routine operations without human intervention. A single engineering officer could supervise reactor operations from a control console that displayed critical parameters and executed programmed responses to transient conditions. The reduced manning decreased life support requirements, enabled smaller pressure hull diameters that reduced hydrodynamic drag, and theoretically improved stealth through eliminating noise sources associated with human activity throughout the vessel. Soviet naval leadership viewed Project 705 as transformational technology that would fundamentally alter the underwater warfare balance. Admiral Sergei Gorshkov, Commander-in-Chief of the Soviet Navy, advocated for rapid series production to deploy substantial numbers before NATO forces developed effective countermeasures. The first vessel, K, commissioned in December 1971. Production continued at Sudomik and Sevmash shipyards through the 1970s, with 7 submarines ultimately completed. Soviet operational doctrine envisioned employing Alfa-class submarines in sprint and drift tactics, where high speed enabled rapid transit to tactical positions, followed by silent operations during actual weapons employment. The submarines would exploit their speed advantage to penetrate NATO anti-submarine warfare barriers, engage high-value targets including aircraft carriers and ballistic missile submarines, and escape before defensive forces could respond effectively. Western intelligence agencies struggled to assess Project 705 capabilities accurately during early development phases. Human intelligence sources provided fragmentary information suggesting Soviet pursuit of titanium submarine construction and exotic propulsion systems, but reports lacked technical details necessary for comprehensive threat evaluation. Acoustic intelligence from SOSUS detections and submarine tracking operations generated performance data indicating speeds and depths beyond previous Soviet capabilities, but analysts debated whether observed characteristics represented actual operational performance or short-duration sprint capabilities unsustainable during extended missions. The uncertainty generated intense debate within U.S. Navy leadership regarding appropriate responses. Some officers argued that Project 705 represented desperate Soviet attempt to achieve tactical advantages through technological gambles that would prove unreliable in actual combat. Others concluded that Soviet engineering had achieved genuine breakthrough requiring immediate countermeasures. The CIA's Office of Scientific Intelligence initiated comprehensive analysis, examining all available data on Project 705. The assessment compiled in 1974 concluded that Soviet claims regarding alpha performance were substantially accurate. The titanium hull was real, the liquid metal reactor functioned as described, and the speed performance exceeded 40 knots sustained with burst capability approaching 45 knots. The intelligence assessment warned that existing NATO torpedoes could not reliably engage Alfa-class submarines. The primary American anti-submarine torpedo, designated MK47, achieved maximum speed around 26 knots with effective range near 10,000 yards. An Alpha submarine detecting torpedo launch could simply accelerate and outrun the weapon. The improved MK48 torpedo entering service in 1972 offered better performance with speeds approaching 55 knots and range exceeding 20,000 yards. But guidance systems lacked sophistication necessary to maintain track against targets, maneuvering violently at extreme depths while employing acoustic countermeasures. U.S. Navy leadership confronted operational reality that Soviet technological audacity had created genuine capability gap, requiring urgent response. The Chief of Naval Operations directed initiation of the MK48 Advanced Capability Program, designated ADCAP, in 1975 with specific requirements targeting Alfa-class capabilities. The improved torpedo needed speed sufficient to chase targets exceeding 40 knots, guidance systems that maintained accurate tracking through evasive maneuvers and countermeasures, warhead lethality adequate to ensure destruction of titanium hulls, and operational depth capability matching or exceeding alpha diving limits. The technical challenges were substantial. Increasing torpedo speed required more powerful propulsion that consumed fuel reserves faster, reducing effective range. Improved guidance demanded signal processing capabilities beyond existing analog electronics, while operating within volume and weight constraints imposed by torpedo dimensions. Meeting these requirements simultaneously required advancing multiple technologies in parallel. The propulsion solution employed a stored chemical energy system that reacted auto fuel with oxidizer to drive a piston engine generating shaft power. The combustion process produced minimal exhaust signature while delivering power density sufficient for sustained high-speed operation. Engineers optimized fuel formulation and engine configuration to achieve speeds exceeding 55 knots at maximum power settings, with range maintained at useful tactical distances. The guidance system represented more significant innovation through incorporating programmable digital signal processors that enabled adaptive algorithms responding to target maneuvers. The MK48 ADCAP employed both passive and active sonar modes. In passive mode, the torpedo listened for target acoustic signatures, homing on propeller noise and machinery tonals. When passive tracking degraded due to target quieting or countermeasures, the torpedo activated high-frequency active sonar that transmitted acoustic pulses and processed returns to determine target range and bearing. The combination provided robust tracking capability resistant to evasion tactics. The warhead design required destructive power adequate to breach titanium pressure hulls, even with partial hits resulting from last-moment target maneuvers. The ADCAP employed a shaped charge warhead weighing 650 pounds that focused explosive energy into a high-velocity jet capable of penetrating heavy metal structures. The detonation control system included proximity and contact fusing modes with magnetic influence sensors that detected target signatures, even if direct impact was not achieved. Testing demonstrated that ADCAP could reliably destroy submarine targets at depths approaching 800 meters, sufficient to engage Alfa-class submarines throughout their operational envelope. While American engineers developed countermeasures against Alpha capabilities, Soviet submariners discovered that revolutionary technology imposed operational burdens that compromised the tactical advantages speed and depth theoretically provided. The liquid metal reactor cooling system required continuous operation even when the submarine was pier-side. Lead-bismuth coolant solidified at 123 degrees Celsius, and allowing temperatures to drop below this threshold would freeze the coolant throughout the primary system, permanently immobilizing the reactor. K experienced a coolant leak during operations in 1972 that contaminated the reactor compartment with radioactive lead-bismuth. Attempts to repair the leak failed, and the Navy ultimately decided the vessel was unrecoverable. Engineers pumped the entire reactor compartment full of furfural alcohol to seal contaminated surfaces and prevent further corrosion. The submarine was decommissioned in 1974 after only 3 years of service, a testament to maintenance challenges that exotic technology imposed. The automation systems that enabled reduced crew complement introduced reliability concerns that became apparent during operational deployments. Analog control systems lacked redundancy features that digital architectures could provide. Component failures in critical control paths could disable entire systems without warning. K-373 suffered multiple automation failures during a 1976 patrol that forced the crew to operate the submarine in manual control mode, effectively negating the advantages that automation was supposed to provide. The psychological stress on crew members operating revolutionary but temperamental technology in hostile waters proved substantial. Several commanding officers reported that their crews exhibited higher anxiety levels compared to personnel aboard conventional submarines, reflecting reduced confidence in the reliability of systems their lives depended upon. The acoustic signature that Soviet engineers anticipated would remain manageable through speed and depth advantages proved more detectable than doctrine assumed. The compact reactor and high power density generated machinery noise that radiated efficiently through the titanium hull. NATO acoustic analysts tracking Alfa-class submarines reported that while the vessels were indeed fast, they were not particularly quiet at high speeds. The hydrodynamic flow noise generated at 40 knots created acoustic signatures detectable at substantial ranges by advanced passive sonar arrays aboard American attack submarines and maritime patrol aircraft. An Alpha submarine operating at maximum speed essentially announced its position to any adversary within detection range. The tactical doctrine envisioning silent approach, followed by high-speed sprint required transitioning between quiet and fast modes, but this transition itself created detectable transients that alert sonar operators could identify. The economic costs associated with Project 705 construction and operation exceeded even the substantial expenses that nuclear submarine programs typically incurred. Titanium fabrication required specialized facilities and techniques that could not be shared with conventional steel submarine construction lines. The unique liquid metal reactor demanded separate maintenance infrastructure, specialized training programs, and dedicated refueling facilities. When combined with the persistent reliability problems and limited operational availability, the cost per operational submarine patrol reached levels that Soviet naval leadership found difficult to justify. By the early 1980s, the chief of the Soviet Navy questioned whether continuing Project 705 operations provided sufficient value to warrant ongoing investment. The development of MK48 ADCAP fundamentally eliminated the invulnerability that had justified Project 705 existence. When U.S. Navy attack submarines began receiving ADCAP torpedoes in 1988, Soviet naval intelligence quickly recognized that Alfa-class submarines faced credible threats from weapons they could not reliably evade. An American submarine detecting an Alpha could employ ADCAP from ranges where the Soviet vessel might not even know it was being targeted. The torpedo's speed advantage and sophisticated guidance meant that even if the Alpha commander detected launch and initiated maximum speed evasion, the weapon would likely maintain pursuit and achieve kill. The tactical advantage that had defined Alpha capabilities evaporated once adversary technology caught up. The political and economic upheaval that engulfed the Soviet Union during the late 1980s accelerated Project 705 retirement. Defense budgets contracted sharply as the Soviet economy struggled with systemic failures that would ultimately lead to the USSR's dissolution in 1991. Maintaining specialized capabilities that required unique infrastructure became untenable when the Navy faced decisions about which forces to preserve with limited resources. The last operational Alfa-class submarine, K-123, decommissioned in 1996. Several hulls underwent scrapping at specialized facilities equipped to handle radioactive lead-bismuth contamination. K-493 remains in storage at Severodvinsk, preserved as a historical artifact representing a technological path that achieved remarkable engineering success but proved operationally unsustainable. The legacy of Project 705 extended beyond the specific submarines that briefly operated during the Cold War's final decades. The titanium fabrication techniques developed for Alpha construction informed subsequent Soviet and Russian submarine programs. The Sierra-class and later designs employed titanium in critical structures where weight reduction and depth capability advantages justified the expense. The experience with liquid metal reactors provided data that influenced Russian naval reactor development, though no subsequent submarine class adopted the technology for operational service. The automation concepts that reduced crew requirements influenced modern submarine design philosophy across multiple nations pursuing smaller, more capable vessels. For Western naval forces, the Alpha Challenge validated investments in advanced torpedo development and acoustic surveillance capabilities. The recognition that adversary engineering could achieve genuine breakthrough performance forced continued innovation rather than complacency. The MK48 ADCAP program demonstrated that American engineering could respond effectively to Soviet technological surprises, though the response required time and resources that might not be available in actual conflict scenarios. The intelligence community's struggle to assess Alpha capabilities accurately during early development highlighted the importance of technical collection against adversary research and development programs. The confidence Soviet naval planners invested in speed as the ultimate submarine defense collapsed when American engineers developed weapons that could catch even the fastest underwater vessel. The presumption that titanium hulls and liquid metal reactors represented unbeatable technology failed when operational realities revealed maintenance challenges and reliability problems that exotic systems inevitably produced. The tactical advantage that 43-knot sprint speed theoretically provided evaporated when the weapon hunting it could travel at 55 knots with guidance systems that maintained track through violent evasion. Project 705 proved that engineering audacity could achieve remarkable performance characteristics, but technology alone could not deliver sustained operational advantage when adversaries possessed resources and determination to develop effective countermeasures. The lesson that emerged from the depths where Alpha submarines once raced beyond the reach of NATO weapons remained clear. Every technological breakthrough eventually meets a response that eliminates the advantages that justified its creation.